Hello and welcome to the next installment of E&P's Connect, where we sit down and interview leading figures in the offshore oil and gas industry about their insight and opinions on the state of the industry. Joining us today is Don Allen, President of VIV Solutions, and Julie Dehne, Business Development Manager for VIV Solutions. Don, Julie, welcome to the show.
Thank you.
Thank you for having us today.
Please tell us a little more about VIV Solutions.
VIV Solutions is a Houston-based company. We specialize in suppression equipment such as helical strakes and fairings. Don Allen, our president, studied VIV suppression and its technologies at Rice University. He joined Shell and continued his research there. We eventually became part of the Shell Global Solutions Group, and we investigated various uses for fairings and strakes in deep water. And over the years, we continue to invent new suppression devices and add to our growing list of patents. In 2009, Shell elected to dissolve the business. So Don retired, started VIV Solutions, and here we are today. As I touched on earlier, we have 29 patents currently held by VIV Solutions team members, and we have more that are pending. One of the products that we've developed recently is called a standoff strake, and it utilizes a channel to hold the strake spaced away from the pipe body. And this was in direct relation to a project we did where a customer came to us with the requirement of wanting to have seawater flowing between the strake body and the tubular. So the standoff strake product allows that water to circulate, and it's another technological advancement that we've added to the VIV Solutions brand.
Could you please explain what VIV is?
VIV stands for Vortex-Induced Vibration, and most people experience it at a young age in a swimming pool. If you ever try to move your arm very quickly through a swimming pool, it won't go straight. It'll wobble a little bit. The faster you go, the more it'll wobble. And that's their first experience with vortex-induced vibration. And it occurs anytime you have a fluid flowing past a long cylindrical or bluff object. That object will experience vortex shedding, which people see usually also at a young age when they put a stick in a stream and they see the vortices going behind the stick. But that alternating vortices, the same pattern that puts vibration on your arm, will put vibration onto a structure in the ocean from ocean currents. So that as that water in the ocean flows by the structure, in our case, we're mostly worried about tubular structures in the ocean, that vortex shedding puts alternating forces on the tubular. And inevitably, those alternating forces, since they're at a certain frequency, which is proportional to velocity, that vortex shedding will match or be close to a natural frequency of the structure. And so now the structure is now self-exciting. It's the amplitude of vibration grows and grows. Fortunately, VIV is self-limiting, but it still can be problematic because of so much vibration that you can get. So anytime a tubular is in the ocean and in an ocean current, VIV is then a concern.
Could you please elaborate further as to why it is a concern?
Well, if I took a paper clip and I bend it back and forth, eventually I'll break it. And while fortunately pipelines in the ocean are not nearly as sensitive to those kind of stresses, we still get the potential for failure due to vortex-induced vibration. And then another issue that is associated with VIV is having too much riser deflection or too much drag. So as a structure vibrates, the drag on that structure goes up. And so if we have too much vibration or too much deflection, then we get too much static stress on the structure. In many cases, for example, for a drilling riser drilling in a current, too much deflection means too much top angle and you have to suspend drilling operations. So that's a concern because time is money for drilling.
So how is VIV managed?
Typically, VIV is managed one of a number of ways. The expensive way to do it is to take my tubular and just pull on it as hard as I can, which reduces the fatigue damage rate that the vortex shedding is causing, and also reduces the deflection of the tubular due to vortex-induced vibration. The less expensive way to solve it is to put on some kind of vortex-induced vibration suppression device. We call it VIV suppression devices. The two most common classes of devices are helical strakes, which are basically fins that wind around the tubular tubular, and fairings, which basically streamline the flow. Helical strakes are commonly seen today on car antennas. So most car antennas have a single start helical strake that's molded into the antenna on the car if it has an external antenna. So you may have seen that. Fairings, again, they look like an airplane wing, but the fairings we use in the oil and gas industry are much, much shorter than an airplane wing because it'd be too cumbersome to use a very, very long fairing like an airplane wing. And actually the short ones work generally better. So we use a short fairing, and the fairings are free to wear. So if the current changes direction, the fairing just rotates with the current. So it's loose on the tubular and it's supported by some kind of collar or clamp that it just sits on in weather vanes. And they'll install these all over a riser oftentimes, or part of a riser. There may be hundreds or even thousands of feet of fairings or strakes on a riser. The strakes are clamped tight on the riser so that they're not free, they don't need to move. Since they're helical, they can work regardless of current direction.
So what are some of the challenges you are seeing in industry surrounding VIV?
I think every project tends to be different, which is a bit surprising. We'll build a given helical strake or a fairing for a project, and we think, okay, we'll just be able to build that the same way the next time. And it never seems to quite work that way. There's something different about each project, which means quite a bit of engineering and design work that often goes into the design of the helical strake or fairing. For example, the riser may be insulated, and therefore the outside diameter of that tubular is going to shrink with depth due to hydrostatic pressure. So whatever is clamped tight on that riser, whether it's a helical strake or it's a clamp or collar for a fairing, it's got to be able to adapt to that change in diameter, which is going to now be different all along the depth. We recently had a project we did for Mars B for Shell, where we had to S-lay fairings. And S-lay means the pipe goes over a stinger and makes an S shape in the ocean. And by that pipe going horizontally over that stinger, there's a lot of forces on the suppression devices as that pipe's being installed, because it has all the weight and tension of the pipe on it. And we not only did we have to do that, but the riser was insulated, so it was going to shrink due to hydrostatic pressure. So we had to have a collar that could both go over the stinger and take all those forces, but at the same time, the collar had to be able to stand hydrostatic pressure. Every project tends to be a little bit different. There's something different from the last project.
How is the transition from deepwater to ultra-deepwater impacting designs of suppression systems?
I think what we see more than anything is they're using more of them. As companies went into deep water, they suddenly encountered ocean currents that were more persistent and of greater magnitude than what they had encountered in the past. And so that's when really the pioneering work of VIV suppression occurred in the late 80s and 90s. There was a lot of research trying to figure out how much suppression do we need to put on, and what does it need to look like, how does it work. And then now the industry is a little bit more mature in that area. Now as we go into ultra deep water, we look at the need for even more suppression. The probability of having a current on site goes up as you go into ultra deep water typically. So what we call the site probability is higher. The maximum currents that we see are higher. So you have both more duration and greater magnitudes of ocean currents. So because of that, we see more and more use of VIV suppression devices. So instead of maybe needing 1,500 feet per tubular, customer maybe want 3,000 or even 5,000 feet of suppression on a tubular. The other thing that we see is that drag now becomes more and more important. Because if you have an array, for example, an array of tubulars in the ocean that may be 10, 15 feet apart, we don't want the current driving one tubular into another. We want to keep those tubulars separated subsea. And that then makes fairings a more important product than strakes. Early on, helical strakes were just about all that people used. And then as we've seen time go by and we're seeing more march into ultra deep water, we've seen a greater tendency to use fairings on at least part, if not all, of the tubular, because fairings offer about half to 1/3 the drag of a helical strake. So that lower drag means that it's easier to go in deep water. Riser spacings can get smaller, which saves real estate at the surface, and that lower drag then keeps those tubulars from contacting each other.
Does VIV suppression differ in the North Sea or off the coast of Brazil or West Africa? How do those needs differ, or do they differ?
Well, the main difference, I think, is the fact that the currents vary from one area of the world to another. So in the Gulf of Mexico, the predominant feature is the loop current or eddies that spin off of the loop current. That same feature is similar to what's going off the east coast of Brazil. So those areas are pretty similar, probably the areas where we've spent the most focus in the last 15 years on VIV and VIV suppression. For example, the Kuroshio current offshore Japan, which is extremely strong, 6.5 knots. Some people are saying it can get even higher than that.
One thing that can vary with geographical region is the amount of marine growth that a riser may see. So oftentimes we'll design a suppression device to accommodate that marine growth, whether it's a copper strip inside the fairing tail or copper bearing surface for our collars, or we'll sometimes apply an anti-fouling paint to the strake bodies. So we'll see anywhere from 0 to 500 feet of suppression. That's what we call anti-fouling suppression to combat that marine growth.
So with each issue of Offshore Connect, we like to ask the same 3 questions to kind of get a spectrum of answers across the board from the different people we speak with. So our first question is, and both of you please feel free to answer, is what is the biggest challenge that you see facing the offshore industry over the next 5 years?
I would say technology and knowledge transfer is a big key. We see a lot of people in the industry that are preparing for retirement, and a lot of new folks coming in, new engineers. So if there's something that we can do to certainly pass on that information and that rich history, I would definitely encourage it.
What is the technology that holds the most potential as an enabler for ultra-deepwater developments in remote locations?
Probably the application of drilling a well and the new technologies there being applied to the production riser setting. Maybe Don can expand a bit on that.
So what we see is companies going into areas, as I mentioned earlier, where they don't know exactly what the ocean currents are. They still have to deal with the ocean currents there. And one of the products we've actually come up with is a drilling riser fairing solution that's very fast to put on, so that you can put the riser on the water and take it out fairly quickly. And again, time is money, but also the more wells you can drill with the least vessel, the better.
Which industry can the offshore oil industry learn most from, in your personal opinion, for technology transfer?
Well, my background is actually in automotive engineering. I worked for an IndyCar team for a few years, and there was a lot of competition that we would see between major players. So you would have a technology that you would develop in-house, you would bring it to the track, and you tested it. And if it worked, you were on the podium and you were in the winner's circle and you were excelling. And if it failed, you'd have to go back to the drawing board and start again. So I think that that's something that big oil can learn from in the oil industry, is that a bunch of the major operators can push each other as far as improving upon existing technologies and making things better for the future.
Coming from a background where I started off as a researcher and have gone all the way now to manufacturing in the industry, is the time to develop and implement technology is many times too long in the industry. And there are good reasons often for that, wanting to make sure that the new technology is safe to use and that it really is better than what's being used now, and just making sure that new technology is properly vetted. But at the same time, I think that on average, it takes too long. And I know a lot of companies are working on ways to shorten that length of time. And we ourselves, even internally, are working on how do we shorten the time for our own internal products, where we go from an idea to developing that idea and testing that idea and then implementing that idea, that it's going to be safe to use and that it's going to work well the first time we use it, because it has to work right the first time.
Don, Julie, that concludes our interview today here on Offshore Connect. I want to take this opportunity to thank you both for participating. It's been a pleasure.
Thank you very much.
Appreciate it. Thank you.
And this concludes another installment of E&P's Offshore Connect. See you next time.